Today we will explore how we can solve the problem of generating names with recurrent neural networks. We will have the dataset containing around 8,000 names from different cultures, and these names are transliterated into the Latin alphabet. So, and we will use this data set for training RNN for generating other names, based on catching dependencies from our dataset. Our dataset will be represented as the list of names. Each name is just a string. I want to remind how the RNN model looks like. RNN model are using for being able to process sequences of some tokens, and each token is changing the hidden stage in RNN model, and after that we use this hidden stage and the current token to predict the next token. So, we want to solve the problem of generating names, and we decided to solve this problem using the recurrent neural network. How do you think? In this case, what is a token? Yeah, I need your assumptions. So we want to solve the problem of generating names. Each name is just a string. This containing from different characters, and our model can process some kind of tokens step by step. On each step, we using the previous token for predicting the next token. So in this case, in our task, what is a token? What is a token? Yeah.
An alphabet.
So right way, but not totally not totally exactly, but yeah. So a token in this case is character, but yeah, but our characters are from some alphabet or some vocabulary, yeah, because sometimes names can contain not only letters but some special symbols, for example. So, but yes. So let's read our data set from some file. Yeah, how we can see our data set contains around uh, 8,000 names. Um, the next step, what we want to do, we want to analyze our data set and want to understand the structure of our data set. Uh, for example, we can to plot the histogram um, of name length. Yeah, we want to see on the distribution of name length. How do you think uh, why uh, why is this step important for us? How do you think why is understanding of how length mm, how long our data our examples yeah, why is important to understand that?
So that we can have a better knowledge about how the normal distributions parameter will be.
Yeah, so if we uh, if we start to discuss this current task and with histogram, uh, what can we say about our data, and maybe we can decide that some of data um, are not so important for us, and uh, we can filter this type of data. How do you think? So, if we start to analyze with this distribution of lengths, we can notice that um, there is um, a few examples of names containing more 10 characters. Uh, just really a couple of examples. And how do you think using these really poor number of examples of long names, can we train good, correctly our model or not on these examples? So yeah, if we see some really good tails in our distributions, we can decide uh, to just drop out these examples, because yeah, we we don't have a lot of examples for good training process for long names, and yeah, we can just overfit by these examples. And yeah, and so let's just fill these examples from our data set. Also, um, try to image that we get some data set, these these long texts, and um, we need to choose between two two approaches: RNN, vanilla RNN, and LSTM. So yeah, what approach is more suitable for long texts? Guys, in now we have a really short texts in our data sets, and based on this knowledge, we decided to use RNN, and yeah, because for short text, this simple model can be enough. But if we want to process some long texts, significantly longer, RNN is enough for that, or in this case we will prefer to use LSTM, for example?
LSTM, I guess.
Why?
Because it stands for long short-term memory, so you probably needed to make sure that the model remembers the context of larger sentences.
Yes, and in RNN, what kind of memory we have only? LSTM contains long and short terms memory. Yeah. In RNN, what kind of memory is?
I might think short.
Yeah, only short.
But LSTN is also an RNN.
Yeah. Yeah, now we will use vanilla RNN only with short term memory. Yeah, because we have a data set, these short examples. Yeah, and for this case, yeah, this simple approach can be enough. So I mentioned about that because it it is additional reason to analyze uh, the distribution of lengths, yeah, in your data set, because based on this information can um, you can make a decision about what kind of architecture, yeah, is more suitable for your mm, problem. So, and also, yeah, there are some else additional reasons for analyzing this distribution. Yeah, for example, um, if we um, if we will delete some uh, unusual long examples, we can decrease the computational complexity because yeah, we will see a little bit later um, how we need to preprocess our data, and we will see how the long examples could increase the memory, um, yeah, for storing our batch, and of course it can boost mm, complexity, yeah, in time too. So, and also the last reason it is about quality controlling. Yeah, if our model um, started to generate um, the examples from other distribution um, different from we have, it, it could be a signal for our to about overfitting, and yeah, and we need to uh, double check what exactly happened. Yeah, so sometimes for usually for filtering using percentile. Do you know what is it? Um,
Yes.
Great. So yeah, and you can refresh yeah, using this text. But yes, for filtering our data set, we will use 85th percentile. So, and based on this, um, we need to drop out all examples. What length are more than 9. And yes, this code is just doing that. And yeah, we can see that um, that number of examples in our data set uh, stays the same. But yes, we just deleted some unusual elements. Okay, the next step, we need to understand what vocabulary we have. It needs for filtering and also uh, for representation. Our elements, our items of the sequences as the vector. So, okay, we can just um, go through all names and get unique characters from each name and add to some set. But here we prefer to collect not only unique characters that contain in our dataset, but also count count how how often these characters appear in our dataset. How do you think how we can use this information? Yeah. So I mentioned that we sometimes can use um, the vocabulary and frequency of our tokens for filtering. How do you think how we will use the frequencies of
You remove
characters?
the one that are very little.
Yeah, we you are right. Thank you for answer. So yeah, um, we need to we can plot the distribution of uh, tokens in our data set too. But yeah, in this case, more important for us to see on characters what what appear not frequently in our data set. So yeah, we can just take a slice from yeah, from the uh, left side of our distribution for zooming what happening, and yeah, we can notice that there are some tokens in our vocabulary that that appear less than 10 times. So um, let's understand what token what are these tokens. And yeah, it is a space and yeah, apostrophe. Yeah. And we can we can decide want we be able to generate the names contain two part um, or not, for example. Two part uh, what separated by space. Yeah, we know that uh, there are um, a really uh, poor numbers of these examples, and if we want to be able to generate this type of names, we need to add some more examples in our dataset. Uh, but yes, in this case, we just decided that we don't want to be able to generate this type of names and just will delete these examples too. So here the code for deleting these examples. I hope this code is understandable. So yeah, and after that we need to update our vocabulary again, and yeah, we can see that we have 53 tokens in our vocabulary. So, mhm, okay. After that, depends on this vocabulary. We need to represent our uh, our tokens as vectors. How how can we do that? All right. Hi guys. So we have names. We understand that each token is just a character. We have a vocabulary um, of characters, and after that, we need to vectorize our characters. Yeah, what we need to do. What mm, what approaches are for vectorizing um, categorical features? I think in the lecture, um, the one hot encoding was mentioned, and yeah, for example, we can use this basic approach for vectorizing our tokens. So yeah, before we start to vectorize our uh, our sequences, we need to add to our uh, vocabulary some special symbols. The first source, it is a start of sequence. It's just this special symbol is added um, before each uh, sequence, just to say to model that uh, we need to start generating process. So the second is about saying when we want to stop, and the first it is unmeaningful symbol just um, for add some characters to texts, to names in our case, what length um, are not enough. Yeah. So why we need to why how we can use these first two um, special symbols? For example, why we need to start from this special symbol, um, our training, our generating process. Why we can't to start just this the first character of our sequences. What ideas do you have? It is really simple because to image if we will not to um, add this type of symbol and start training just using our sequences. In this case, we don't have any flag for for asking our model to start uh, generating process from empty stage. For example, in our case of generating names, we will need always to add some first letter of our desired name. But sometimes uh, we don't want to do that. We want to start our generating process from the empty stage. And in this case, this special character is really useful. And what about the second special character, the end of sequence? why do we want to use this character? What can this character do, add to to our generating process? What happen? What happen if we don't add this special character? Guys, what?
We won't know where the sequence is ending. I mean, when the character end and then you won't begin.
So yeah, in this case, all our generating processes um, just can't stop, yeah, because our model will not know when it needs to stop, yeah. So yeah, just remember about that, and that this step of reprocessing your dataset, if you want to solve some generating problem, really important. So yeah, the next code, it is just about adding these special characters. Okay, so yeah, and we can see that if we have um, some examples of these different lengths in one batch. In this case, we always add uh, padding characters to the end of short names. The yeah, like that. Just because we need to get we need to give um, examples these same lengths in the batch, in each batch. So yeah, it is just a visualization about batch, and yeah, before that, when we um, when we discussed about why we need to delete some really long examples. Yeah, because when we process the batch, we need to add some elements for two examples. These short lengths, yeah, based on the most the longest element in our batch. And for example, is if we have some elements are significantly longer than others. On this step, we need to use a lot of memory for creating uh, the batch. So let's go to create the recurrent neural network and to train this architecture for our task. So we need to convert our characters to embeddings to vectors, and after that we need to um, change our uh, hidden stage. Um, Based on this hidden stage and the current token, they need to predict the next token. Yeah, we need to predict predict probabilities of each token in our vocabulary. So yeah, here is the class for implementing our RNN, and yeah, we need to use some layer which are called embedding, and we need to um, represent our our sequences of characters to sequences of vectors. After that, we use some linear layer for changing our this layer. Yeah, this layer is used for changing our hidden stage. We generate new some updates for hidden stage based on our current token and the previous hidden stage. And this linear layer is using for making predictions for uh, getting probabilities of our tokens in our vocabulary. So we need to look to forward process, how we will make predict how we will predict the next token. So first of all, yes, we apply we transform each character to embed. After that, we need to join the current embedding, and this hidden stage. After that, we use a linear layer for updating the current stage, hidden stage. And after that, we apply a non-linear function. In NNs, we use turn. So why? I think in the previous seminar and in lectures, yeah, we heard that um, turn is not a very useful non-linear function in general. But why we need to use this function here? Why, for example, we can't use ReLU?
Why we want to use what?
So, okay, again, for updating our current stage, our hidden stage, we use the linear layer and some non-linear activation function. Yeah? Okay, and in general, we uh, we talked before that in generally, yeah, ReLU is a more useful non-linear function for neural networks because we uh, we have a gradients with more values and yeah, we don't have uh, and our neural networks um, training better this uh, this ReLU as non-linear activation functions. But here we are using ton as a non-linear activation function. So why we don't why we don't use ReLU, and could we use ReLU or not? Yeah. How do you think? Could we just replace ton here to ReLU?
We replace tan with what?
ReLU.
Sorry, I can't understand. Can you write it?
Yeah.
Or
ReLU. ReLU.
because tan is from -1 to 1 and oh wait, it's hyperbolic tan.
Mm-hmm.
Uh,
Of this activation function?
yeah, ReLU is unbounded, I think, right?
Yeah,
That might cause problem.
we don't have the upper boundary, and how um, how can it affect to our training process? Why we want to have a non-linear function or these boundaries?
I think it will have, like, the gradient would be too big if we had infinity there.
Mm, why we can get infinity gradients?
Because ReLU is unbounded.
Yes, but for example, in other type of neural networks, we use ReLU for better training process. Yeah, why we don't use in this type of neural networks?
Okay, okay.
Do you have some ideas? We don't use them because yeah, we have a recurrent architecture. It means that when we uh, when we predict, update the hidden stage H, after this this vector go to input to our network, neural network again. Yeah, and uh, in this case, we need a bounded non-linear activation function because we need to be able to save the distribution of our hidden stage. So, and for example, ReLU, uh, um, yeah, um, on each step, this activation function can increase the values in our hidden stage. And yeah, if we have a really long texts, um, yeah, we can um, get some really big values. Um, and of course, it is bad for linear models, for linear layers. And yeah, we know that when when we are working these linear models, we prefer to normalize our data. And yeah, we talk about batch normalization. Yeah, because we want to save the distribution of our input data. Yeah, in this case, in the recurrent architecture, the hidden stage is a input data too. So we need to some transformation which can save the distribution in the distribution in our hidden stage. So yeah, based on this, we need to use some bounded non-linear function. So yeah, and after that, when we get the next hidden stage, we can to predict the probabilities of characters, and yeah, decide, and based on these probabilities to choose the next character. Okay, here. And yes, here we just how we can initialize the zero stage. So yes, this class just represents the simple vanilla RNN. Okay, after that we need to see how we will be train our model. And yes, first of all, we need to create batch. We need to create batch and represent this batch as a matrices, as a matrix, because yeah. So we each example in the batch, it is a sequence of vectors. So each example is a matrix. And we have some examples in our batch. So our batch can be represented as a three-dimensional tensor. You can see it here. Okay. So about training process. In our train dataset, yeah, we have some sequences, and on each step, we get the current character and try to solve classification problem. Why classification problem? Because yeah, because we just have a categorical features, and we need to understand what yeah, we just need to predict probabilities of each categorical features. In our case, of each characters in our vocabulary. So yeah, it is just a classification problem. So we can use cross entropy loss, and yeah, and we know the next character, and yeah, we just can compare the next character and what we predicted. And yeah, really, really simple idea. So yes, and based on this information, mm, we can make uh, one optimization step. Yeah, using backpropagation. We discussed about uh, how we can use this approach for training neural networks in the previous seminar. So yeah, here you can find the loop for training. Yeah, we need to select a batch. We need to try to predict the sequences using our models. After that, we need to compare what we predicted, these what they are, using cross entropy as a loss function, and yeah, uh, just uh, just use method backward step and zero graph. And yeah, here as um, our training process looks like not very smooth. Uh, so, but we always can to try to make this training process more smoother using different parameters in our optimizer. For example, changing learning rate. Here we use the standard learning rate and use Adam. But yes, we can try to make this process smoother, but it is about validation process and to try to find better hyperparameters. Okay, and after that we trained our model, we can start to play this our model and start to generate examples. Yes, this code for generating examples. Yeah, we just if we want to start uh, from empty stage, we can give a source character to our neural network and yeah, and generate each next character step by step. And yeah, and after each generating a step, we need to check um, the current character is the character of ending our sequence or not. And yeah, if we meet this special character, we need to stop our generating process. And so, yeah, for make predictions, we can use the softmax. Um, okay, I think you understand. I hope you understood how we can generate some sequences using our trained model. Here is examples of generated sequences. Yeah, we said that we can start from empty stage, but we can start from some other stages. For example, we can get 1, 2, 3 uh, first letters, and yeah, and to see what our model can add after that, these letters. Yeah, we can use our model in this setting too. We need to discuss now the last thing about this parameter, temperature. So let's see about our generating process. Yeah, okay. We are using our RNN for on each step to get hidden stage and Legitz for making predictions. So yeah, and after that, for making predictions, we the use this temperature parameter. Just we make our logits more or less using this temperature parameter. And how do you think how this change can influence for our generating process? So our we can predict something in the following way. So first of all, we use some linear transformation in our RNN. Yeah, and after that we apply softmax to this vector, and yeah, softmax can give us the probabilities of characters in our vocabulary. And yeah, and based on these probabilities, we can choose the most yeah, we can choose the next character. Of course, we can choose the next character as a just get the character this the this biggest probability. Of course, we can use this knowledge uh, as a probabilities distribution and try to make decision this sum uh, this sum random. Uh, but yes, but before we uh, we transfer vector after linear transformation, we can use this parameter temperature for increase or decrease these values. Yeah, and after that we transform these values to the distribution of probabilities. So how do you think if we will use the really higher temperature, uh, how how it can influence to our generating process? Yeah, this parameter we can use for change. So for changing uh, our resulting distribution of probabilities. For example, we can make the biggest probabilities more bigger, and or we can make our distribution of probabilities more smoother, and depends on this our generation will be more chaotic or less chaotic. For example, here we uh, we get many same examples because we don't have um, because we really decrease our uh, chaotic process. So we if we use a bigger um, temperature, in this case, we will create our final distribution of probability more smoother. So, um, and in this case, we will have more chances to select different characters. Yeah, because for example, if we have some characters with really high probabilities using the high temperature, we divide uh, these probabilities and uh, make our final distribution smoother, and we have more characters with these same chances to be chosen. And yeah, in this case, our generating process will be more chaotic. And uh, if we, for example, will use this temperature, we will have more different examples after generating. Yeah, I hope uh, this clear now how we can use this parameter for for decrease or increase chaotic in our generating process. And yeah, of course, now uh, we realized RNN from scratch, but of course there there's classes for that. In Torch you can use RNN cell, RNN, LSTM cell, RU cell. Yeah, we don't need uh, to develop each time this architecture from scratch. Yeah, you can just uh, transform your tokens to embeddings, and after that just use RNN cell for yeah for your architecture. And yeah, so that's all. Thank you for your time. Do you have any questions about?
Yeah, so when the temperature is like 10, we'll get randomness basically, right?
Yeah, sorry,
Okay.
I can't run now this code because we need to run from first
Yeah.
cell. But yes, you, I will share this notebook in chat, and yeah, you can try to run all cells, and yeah, if you start to um, increase temperature, you will start to get more different examples after generating process. So, do you have any questions? Yeah, thank you. Thank you for your time.
Thanks for the seminar.
Thank you. Bye. Bye, guys.